Thermal expansion of materials. Thermal expansion of materials. By heating, we know that all substances will expand. All substances will expand on heating. But in case of water, water contracts from 0 degrees centigrade to 4 degrees centigrade. Beyond 4 degrees centigrade, it expands. So, except water, the two in the range 0 degrees centigrade to 4 degrees centigrade, all substances expand. In case of solids, we study this expansion in the form of linear expansion, areal expansion and volume expansion. In case of solids, the expansion is studied in three ways: linear expansion, areal expansion and volume expansion. In case of liquids, we study only volume expansion. In case of liquids, we study only volume expansion. In case of gases, we study the expansion in two forms. One is pressure change at constant volume. We study change in pressure with temperature at constant volume and change in volume with temperature at constant pressure. So, we study pressure change at constant volume and volume change at constant pressure. Like this, we study the expansion of materials. In solids, atoms are arranged at regular intervals. In solids, atoms are arranged at regular intervals. Their interatomic distance is constant. Their interatomic distance is constant. They vibrate about their mean position. The atoms vibrate about their mean position and the force between atoms is maximum. The force of attraction between atoms is maximum, so that the potential energy is a minimum. The energy between the atoms will be minimum. The interatomic distance depends on temperature. The interatomic distance depends on temperature. Hence, a solid is considered as an assembly of vibrators. A solid is considered as an assembly of vibrators. With the increase in temperature, the energy of the atoms will increase. The energy of the atoms will increase, but the distribution of energy is not harmonic. Such a situation is called enharmonicity. Due to this enharmonicity, the interatomic distance increases. The interatomic distance increases due to enharmonicity. To understand this concept, let us use the graphs. By drawing graphs between interatomic distance and interatomic potential energy, we study enharmonicity. In the first graph, you notice a parabola. On x-axis, interatomic distance is taken. On y-axis, interatomic potential energy is plotted. And you notice a parabola which is symmetric. Here, the vibrations are harmonic and potential energy curve is symmetric. On the right side, you notice another graph. In this graph, the curve is not symmetric. The non-symmetric curve indicates that the potential energy is not distributed symmetrically. So, the interatomic distance increases. R0 indicates the equilibrium state, and as the temperature increases, the interatomic distance changes to R1, R2, R3, R4, etc. This will happen because of enharmonic distribution. So, the potential energy function is asymmetric and the vibrations are enharmonic. Thereby, the interatomic distance increases. The reason for thermal expansion. On heating a solid, if the vibrations are harmonic, the mean position remains constant. On heating a solid, if the vibrations are harmonic, the mean position remains constant. The vibrations are enharmonic. If the vibrations are enharmonic, then the mean distance between atoms increases. The mean distance between atoms increases. So, expansion takes place only when the mean distance increases. Only when the mean distance increases. So, there should be increase in mean interatomic distance so that expansion takes place. Coefficient of linear expansion. Coefficient of linear expansion. The symbol is alpha. Symbol is alpha. You have already studied the relation for coefficient of linear expansion in your 9th class. If we take a metallic rod of length L1 and its temperature is say T1, when it is heated to temperature T2, suppose its length becomes L2, its length increases, L2 is greater than L1. So, the coefficient of linear expansion alpha is given by L2 minus L1, that is increase in length, by L1 original length into T2 minus T1 rise in temperature. The relation for alpha is L2 minus L1 by L1 into T2 minus T1, and the definition of alpha is defined as the increase in length per unit length, the increase in length per unit length per 1 degree centigrade rise in temperature, per 1 degree centigrade rise in temperature. By rearranging the above relation, alpha is equal to L2 minus L1 by L1 into T2 minus T1, we get the relation L2 is equal to L1 into 1 plus alpha into T2 minus T1. L2 is equal to L1 into 1 plus alpha into T2 minus T1. Coefficient of areal expansion beta. Coefficient of areal expansion beta. The relation for beta is A2 minus A1 by A1 into T2 minus T1. Here we have to imagine a metallic plate of area A1 having uniform thickness, a metallic plate of area A1 whose temperature is T1. If it is heated to the temperature T2, suppose its area becomes A2. A metallic plate of area A1 at temperature T1, on heating its area becomes say A2 at temperature T2, then beta is given by A2 minus A1 by A1 into T2 minus T1. Then beta is given by A2 minus A1 by A1 into T2 minus T1, where beta is coefficient of areal expansion and it is defined as the increase in area per unit area per 1 degree centigrade rise in temperature. Beta is defined as the increase in area per unit area per degree centigrade rise in temperature. Like this we define beta. For isotropic solids, beta will be approximately equal to 2 alpha. Beta will be approximately equal to 2 alpha. Definition of gamma. Definition of gamma. The relation for gamma is given as gamma is equal to V2 minus V1 divided by V2 minus V1 divided by V1 into T2 minus T1, V1 into T2 minus T1, where V1 is volume at temperature T1, V1 is volume at temperature T1, V2 is volume at temperature T2, V2 is volume at temperature T2. So, gamma is defined as the increase in volume per unit volume per degree centigrade rise in temperature, For an isotropic solid, beta is equal to 2 alpha and gamma is equal to 3 alpha. Beta is equal to 2 alpha and gamma is equal to 3 alpha. Moreover, alpha is to beta is to gamma is equal to alpha is to beta is to gamma is equal to 1 is to 2 is to 3. 1 is to 2 is to 3. Relation for increase. The increase in length is given by E is equal to L alpha theta, where L is original length, alpha is coefficient of linear expansion, theta is increase in temperature. Similarly, the increase in area small a is equal to capital A into beta into theta, capital A into beta into theta, where capital A is initial area, beta is coefficient of areal expansion, beta is coefficient of areal expansion, and theta is rise in temperature, Similarly, the increase in volume is given by small v is equal to capital V into gamma into theta, small v is equal to capital V into gamma into theta, where capital V is initial volume, gamma is coefficient of cubical expansion, theta is rise in temperature, Examples of linear expansion or applications of linear expansion. We know that gaps are provided between rails. This is because to allow the expansion of the rails, during summer, during winter they contract and the length becomes less, so gaps will be widened. During summer the gaps will be closed because of the expansion of the rails. We notice the telephone wires to be hanging during summer. The telephone wires will be hanging during summer because of expansion. Because of linear expansion, the length increases, hence they hang loosely during summer. Similarly, we attach an iron rail to a wooden wheel, to the wooden wheel of the cart, by heating the iron rail. Before attaching the iron rail, it will be heated to a high temperature so that its diameter increases, and then it can easily slip onto the wooden wheel. By heating it. And we use inverse steel for tapes. For measuring tapes, inverse steel is used because its coefficient of linear expansion is less and there will be no change in its length due to the variation in temperature. That is why inverse steel is used for measuring tapes. Chimney glass breaks on sprinkling drops of water. Chimney glass breaks. This is because of uneven expansion. The outside surface will be contracted because of the water drops. It gets contracted, and the inner surface will be in expansion state. Hence, the chimney glass breaks because of the water drops. So, the chimney glass breaks because the outside surface contracts and the inner surface is in expansion state, hence it breaks. So, the chimney glass breaks by sprinkling drops of water. We select platinum to fuse into the glass. We select platinum to fuse into the glass because the linear expansion of platinum, the coefficient of linear expansion of platinum is almost equal to the coefficient of linear expansion of glass. Since the expansions of platinum and glass are nearly equal, platinum is chosen to fuse into the glass.